Dear 12th standard students, today we are going to see the topic phase difference and path difference. Phase difference and path difference is associated with the wave. Phase is a property of a wave. Path also is a property of a wave. See, the electromagnetic wave travel through air or vacuum or free space and also medium. When the wave strikes any medium, each and every particles of the medium vibrate. During its vibration of the particles of the medium, waves are originate and propagates through the medium. Now, we are mainly focused phase difference of a wave and the path difference of a wave. For we assume for a single wave, phase of a wave and the path of a wave. We compare the two waves, we see the phase difference between two waves and the path difference between two waves. Let me assume only one wave is propagated through the medium or propagated through air or vacuum. As a wave progresses, what happens? Path of a wave and the phase of a wave. So, first, before going to see the phase difference and the path difference, what is phase of a wave? Phase of a wave is defined as angular position of the vibration of the particles of the medium. That is called phase of a wave. Here, as a wave propagates, during its propagation, this is one complete wave. During its propagation, I consider this is one complete wave. 0, pi, 2 pi. This is phase of a wave. Distance traveled by the wave during its one complete vibration of the particles of the medium is lambda. Or distance covered by a wave when particles complete one oscillation in that medium. It is called wavelength of a wave. Now we can relate the phase of a wave. Phase of a wave and path of a wave. See, when the wave creates a disturbance in the medium, every particles of the medium oscillate. I consider only one particle receives the energy from that wave, that particle oscillates. When the particle oscillates from equilibrium position to maximum displacement, again comes to equilibrium position, it goes to the negative direction maximum, goes to the equilibrium position. If particle completes one oscillation, during that moment, wave completes one wave. So, distance traveled by a wave when particle completes one oscillation is called wavelength of a wave. So, path covered or distance covered by a wave, one complete oscillation of the particles of the medium is lambda. Path is lambda. At that moment, corresponding phase of a wave, 2 pi. Now we can express one relation connecting in between path of a wave and the phase of a wave. So, distance covered by a wave, one complete oscillation of a wave is lambda. That is called path. Simultaneously, corresponding phase of a wave is 2 pi. Then we can relate the path and the phase. Lambda, which is equal to 2 pi. This is path covered by a wave, one complete oscillation of a wave, which is equal to corresponding phase 2 pi. Then, I don't know that at that instant, path covered by a wave is delta, corresponding phase of a wave. This is path covered by a wave at any one instant during its vibration of the particles of the medium, waves are originate. At that instant, distance covered by a wave or path covered by a wave is delta, then what is the corresponding phase of a wave? Corresponding phase of a wave is represented by pi. So therefore, path at that instant delta, which is equal to corresponding phase of a wave pi. So equation number 1, this is equation number 2. From these two equations, we can connecting the simple relation between phase of a wave and the path of a wave. Equation 2 divided by equation 1. Equation 2, pi divided by 2 pi, which is equal to delta divided by lambda. In our aim to determine the relation connecting in between phase of a wave and the path of a wave, pi, which is equal to 2 pi divided by lambda into delta. So it's a very important relation connecting in between phase of a wave and the path of a wave. We assume a single wave, path covered by a wave delta, corresponding phase of a wave is pi. Already we know that the wavelength of an electromagnetic wave, we can easily calculate the phase of a wave if you knowing the path covered by a wave. For example, simple problem. Path covered by a wave, delta, which is equal to lambda divided by 2. What is the phase of a wave at that instant? We can calculate from this equation pi, which is equal to 2 pi divided by lambda into delta. So pi, which is equal to 2 pi divided by lambda into delta value. Path covered by a wave is lambda divided by 2. So lambda get cancelled, 2 get cancelled. Phase of a wave at that instant is pi. So it is a simple relation connecting in between phase of a wave and the path of a wave. We assume there are two waves propagated through the medium. What is the phase difference of a wave and the path difference of a wave can be calculated from this equation also. That is phase difference and the path difference. Dear students, keep it in your mind. What is phase of a wave? Phase of a wave is defined as a angular vibration of the particles of the medium at that instant is called phase. So in the constructive interference, when it will happen constructive interference, there are two waves meet at this point in phase with each other. Resultant displacement of the particles of the medium is maximum, and at that point should be appears bright. Then the type of interference is said to be constructive interference. In the constructive interference, path difference between two interfering waves delta, which is equal to n lambda. Here n is equal to 0, 1, 2. If path difference del is equal to 0, path difference del is equal to lambda, path difference del is equal to 2 lambda, it goes on. So if two waves are interfere at that point, there is no path difference between two interfering waves, then the point it should appears bright. Then the type of interference is said to be constructive interference. Not only 0 path difference, and the path difference between two interfering waves is lambda, and also 2 lambda at that point it should be appears bright. Then the interference is said to be constructive interference. What is corresponding phase difference between two waves? Pi, which is equal to n into 2 pi. If n is equal to 0, what happens? Phase difference between two waves is 0. If n is equal to 1, So pi is equal to 1 into 2 pi, which is equal to 2 pi. Phase difference 2 pi. Then pi, which is equal to n into 2 pi. Here n is equal to 3. Pi is equal to 3 into 2 pi. So pi, which is equal to 6 pi. So here 1 into 2 pi. Pi is equal to 0. 2 pi. Then 6 pi. The next one, n is equal to 4. Pi is equal to 4 into 2 pi. That is, pi is equal to 8 pi. In this condition, waves are meet at this point. Phase difference 0, 2 pi, 6 pi, 8 pi. In this condition, then the point should be appears bright. Then the type of interference is said to be constructive interference. Then destructive interference. See the students, when the two waves are meet at this point out of phase with each other, resultant displacement of the particles of the medium is minimum, and waves are meet out of phase. At that point should appear dark. Then the type of interference is said to be destructive interference. Condition for destructive interference: path difference between two interfering waves del is equal to 2n minus 1 lambda by 2. Here n is equal to 1, 2, 3. So path difference del is equal to lambda by 2, 3 lambda by 2, 5 lambda by 2. It goes on like this. So in this condition, path difference between two interfering waves at that point lambda by 2, that point should appear dark. 3 lambda by 2, that point should appear dark. 5 lambda by 2, that point should appear dark. So what is the corresponding phase difference between two interfering waves? Pi, which is equal to 2n minus 1 pi. So here substitute n is equal to 0. Not here n is equal to 0. In the destructive interference, n is equal to 1. Pi is equal to 2 into 1 minus 1 pi. Pi is equal to 2 minus 1 pi. Pi, which is equal to pi. So both the waves are interfere at that point. Phase difference between two waves pi at that point should appear dark. Then in the second case, n is equal to 2. Pi is equal to 2 into 2, 4 minus 1, 3 pi. So then pi is equal to 5 pi. So pi is equal to 7 pi. In this condition, waves are meet at that point out of phase with each other. Then the phase difference pi, 3 pi, 5 pi, 7 pi. In this condition, both the waves are meet at that point with that phase difference like this. Pi, 3 pi, 5 pi, 7 pi. Waves are meet out of phase. Resultant displacement is minimum. At that point should appear dark. Then the type of interference is said to be destructive interference. In this way, we discussed path difference and the phase difference. So as a wave progressing through the medium, for a single wave, what is the path of a wave and the phase of a wave? Path covered by a wave is at that instant. What is the simultaneously corresponding a phase covered by a wave or phase of a wave? We assume there are two waves is progress through the medium. What is the path difference between two waves and the corresponding phase difference between two waves? You see the students, it's a very, very important concept in wave optics. Phase difference and path difference. It can be applicable to the constructive interference and the destructive interference. So dear students, now we see another topic in wave optics. Coherent sources. What is coherent sources? See, any source which emits a light is called source of light. Let us consider there are two sources of light. It is the one point source of light S1. It is the another point source of light S2. If both the source of light emits a light waves. That light waves has same in phase or constant phase difference during its propagation. Both the wave has the same amplitude and the same waveform and also same frequency or wavelength. If it will happen, then the two sources of light S1 and S2 are said to be coherent sources of light. So keep it in your mind. First one source of light emits a light waves like this. Second source of light emits a light waves. Both the source of light emits a light waves. Then both the waves are in phase with each other, or during its propagation constant phase difference between the two waves, and also both the waves has the same wavelength or same frequency, and also waveform also same, and same amplitude of a wave, then both the sources of light is said to be coherent sources of light. In these coherent sources of light is required to produce sustained interference pattern in the laboratory. For example, there are two independent monochromatic sources of light. This is S1, another one source of light S2. These two sources of light which is independent. There are two independent monochromatic light source emits a light waves, but both the light waves has the same frequency or wavelength, maybe same amplitude, maybe same waveform, but the waves are not in phase with each other or constant phase difference between each other, because atoms in that source will not emit the light waves in phase with each other or constant phase difference between two waves. Why? Because the atoms will not emit the light waves or not in phase due to the thermal vibration of the atoms in that source. Then the two independent monochromatic light source cannot behave like a coherent light source. See, why two independent monochromatic light source does not act as a coherent light source? Both the monochromatic light source emits a light waves of same wavelength or same frequency, but waves are not in phase or constant phase difference. Why? Because the atoms in that source will not emit waves in phase with each other or constant phase difference. That's why these two independent monochromatic light source does not behave like a coherent sources. But we need a coherent sources to produce sustained interference pattern in the laboratory. There are three techniques. We have three techniques to produce coherent light sources. First one, intensity and amplitude division. Second technique, we produce coherent light source, wavefront division. Third technique is used to produce coherent light sources, source and image. These three are the important techniques to produce coherent light sources. First, we are going to see the first technique to produce coherent light sources, intensity and amplitude division. See the diagram. It is a monochromatic light source. partially silvered mirror. Then another mirror. Then one more mirror. Half silvered mirror. See, we have a single source of light, monochromatic light source. Waves coming from the monochromatic light source allowed to fall on a partially silvered mirror. Here, reflection and refraction simultaneously takes place. Refraction takes place like this. Simultaneously, refraction also takes place. After that, here also reflection takes place. Here also reflection takes place by the mirror. So, both the light beams, this is the one of the light beam, it is the another light beam. These two light beams are two coherent sources. Coherent light beams. See, we have only one monochromatic light source. When light is allowed to fall on a half silvered mirror or partially silvered mirror at this place, reflection and refraction simultaneously takes place. So, reflected wave and refracted light beams reflected by the two reflecting mirror. So, after reflection, both the light beams are coherent light beams. Because why these two light beams are coherent light beams? These two light beams has the same wavelength, same frequency, same amplitude. Both the light beams are in phase, maybe both the light beams having a constant phase difference between each other. Then the two light beams is said to be coherent light beams. In this way, we produce two coherent light source. So, it is one of the technique to produce two coherent light source, intensity and amplitude division. We have only one single source, monochromatic light source, but there are two coherent light source beams. So, in this method, we produce two coherent light beams. Using these coherent light beams, we can produce interference bands on the screen in the laboratory. So next technique, we produce two coherent light source, wavefront division. It is a commonly method or technique to produce coherent light source, wavefront division. How we produce two coherent light source in this technique? See, only one monochromatic light source. There are two narrow slits. S1 and S2 are the two narrow slit. It is one of the slit, narrow slit, it is another narrow slit. That monochromatic source of light emits a light waves. That light wave is propagated towards right. See, that light waves originating from the monochromatic light source towards right reaches the S1 slit and the S2 slit. It covers equal distance from the monochromatic light source. And one more thing, A point source of light at a finite distance produces a spherical wavefront. At every point on the spherical wavefront are in phase with each other. We assume one spherical wavefront strikes both the narrow slit S1 and S2. We assume there are 2 points. On the narrow slit on a given spherical wavefront, both the points are in phase with each other. Then after that, waves are originating from the S1 slit like this. Waves are originating from the S2 slit like this. So after that, then the waves are originating from S1 and S2. Then these two waves coming from both the narrow slits are in phase with each other. Maybe constant phase difference between two waves. Both the waves has the same wavelength or same frequency and also same amplitude. Then S1 slit and the S2 slits, then the two slits act as a two coherent light source. Already we have only one monochromatic light source. Waves are originating from the monochromatic light source at that. A point source of light at a finite distance produces spherical wavefront. One important thing, at every point on the given wavefront may be considered as a source of secondary wavelets according to Huygens principle, and also at any point on the given spherical wavefront are in phase with each other. One spherical wavefront striking the two narrow slit S1 and S2 in phase with each other. Why? Because then the 2 points are at the same distance from the monochromatic light source. Then the secondary wavelets are originating from S1 and S2 spread out in the other medium or towards the right side with that same phase or maybe constant phase difference and the same amplitude and or same wavelength or same frequency. Then the two sources of light S1 and S2 is said to be two coherent light sources. In this way, producing two coherent light source by the wavefront division technique. In this, two coherent sources of light is used to produce interference bands on the screen. Next, one more method to produce two coherent light source. Source and the image. So it is another technique we produces two coherent light source. Here, source produces image and the source and its image act as a two coherent light source. Why? Because both light waves coming from the source and the image waves are in phase with each other or constant phase difference, maybe same wavelength or frequency and the same amplitude and also same waveform. Then these we achieved two coherent light source in this manner, source and the image. So source produces waves and also forming the image. That image also will have a wave and both the wave are in phase or constant phase difference. Then in this technique we produces two coherent light source. Example, Fresnel biprism experiment produces two coherent light source by the technique of source and the image. And also Lloyd mirror produces two coherent light source in this manner, source and the image. First see how two coherent light sources produces in the Fresnel biprism experiment. It is a biprism. Screen. Then one source of light. So waves coming from the source of light. This is overlapping region. Biprism. It is a Fresnel biprism experiment, contains biprism, source of monochromatic light, then screen. When light coming from the monochromatic light source is made to fall on a biprism, after refraction, see that all refracted rays. But all refracted rays extended in the same side of the biprism. This is S1 in that other side. So S1 and S2 is a virtual image. Because these all refracted rays appears to be intersect in the same side of the biprism, it will form a virtual image in that either side of the biprism, S1 and S2 are the virtual image. So S1 and S2, that the virtual images is act as a two coherent light source in the source and the image. In that Fresnel biprism experiment, there are two virtual images produces, there are two virtual images act as a two coherent light source. So here, in these two virtual images act as a two coherent light source. Why? Because both the virtual images have a wave, that waves are in phase or constant phase difference with each other. That's why these two virtual images are said to be two coherent light source. In the same manner also, Lloyd mirror also produces two coherent light sources. In the Lloyd mirror, source and the image, source produces light waves forming an image. So that image wave and the source produces light waves. Both the light waves are in phase or constant phase difference with each other, and also will have a same frequency or wavelength and also same amplitude. Then the produces coherent light source. In this manner, producing the two coherent light sources is used to producing the sustained interference pattern in that science laboratory. So dear students, next one important topic in the wave optics, how double slit act as a two coherent light sources. See, one monochromatic light source, we have a single monochromatic light source, then the single monochromatic light source emits a light waves. That light waves alternate towards the right side. This thick continuous lines is shown by the crest of a wave. Discontinuous lines shown by trough of a wave. Both then the waves are originate towards right side from a single monochromatic light source. Then the light waves strikes a two narrow slit, S1 and S2 are the two narrow slits. After that, at every point on a given wavefront may be considered as a source of secondary wavelets. At the 2 point on a given wavefront, spherical wavefront are in phase with each other. After that, waves coming from the S1 source and waves coming from the S2 source is propagates towards right side in the medium. See, waves originate from the two S1 source and the S2 source. Both the light waves are interfere with each other in space at every point. Here, light wave coming from the S1 source and light wave coming from the S2 source, crest of one of your wave meets crest of another wave, waves are meet in phase with each other. See, thick continuous lines is shown by crest of a wave, or crest of a wave is shown by thick continuous line. So it is a crest of a wave coming from the S1 source, crest of another wave coming from the S2 source interfere with each other at that point, waves are meet in phase. Resultant displacement is maximum. Then the point should appear bright. Then the type of interference is said to be constructive interference. Another one, trough of one of your wave meets trough of your another wave. See, trough of your one of your wave meets the trough of your another wave. Waves are meet in phase. Resultant displacement is maximum. At that point appears bright. Then the type of interference is said to be constructive interference. So from this, we can define what is constructive interference. Constructive interference means at that point where crest of your one of your wave meets crest of your another wave. Trough of your one of your wave meets the trough of your another wave. Waves are meet in phase. Resultant displacement is maximum. Then the point should appear bright. Then the type of interference is said to be constructive interference. Then these all points crossed mark is said to be constructive interference. On the screen, the point appears bright. Then see, crest of your one of your wave meets trough of your another wave, like that. Trough of your one of your wave meets crest of your another wave. Waves are meet out of phase. Resultant displacement is minimum. At that point should appear dark. Then the type of interference is said to be destructive interference. So what is a destructive interference? Light waves coming from the one source, light wave coming from the another source, both the light waves are meet at that point is out of phase. Where? So crest of your one of your wave meets trough of your another wave. Trough of your one of your wave meets crest of your another wave. Waves are meet out of phase. Phase difference between two interfering waves is 180 degree or the radian pi. At that point, then resultant displacement is minimum. Then the point should appear dark. Then the type of interference is said to be destructive interference. See, in this point is a destructive interference takes place. On the screen, that point appears dark. So on the screen, alternatively, dark and bright fringes are observed. Then the fringes are said to be interference fringes or interference bands. Then the entire bands or fringes is entirely due to light waves coming from the two coherent sources overlap or interfere with each other, produces certain points should appear bright, certain points should appear dark, depending upon the path difference between two interfering waves. In this way, we produces interference bands on the screen with the help of two coherent light source S1 and S2. Therefore, S1 and S2, there are two narrow slit act as two coherent light sources. We have only one monochromatic light source. With the help of two narrow slit, we produces two coherent light sources. After producing coherent light beams or coherent light waves, we can produce as interference bands on the screen. Then the bands are said to be interference bands or interference fringes. Alternatively, on the screen, dark and bright fringes are observed. That fringes are called interference fringes. So, dear students, next video class we will see Young's double slit experiment. Briefly, we will discuss later.